This is topic 1.7, and it's on periodic trends. So we looked at this last year in our first year class, and we did a lot of the heavy lifting last year, but I do want to spend some time talking about periodic trends in depth because the way in which you describe and explain them is very important. There's some foundational concepts that we're always going to need to refer to when we talk about these patterns. So it all starts back with the development of the periodic table and Mendeleev. And if you want to scan that QR code for a little bit more information on him, that would be great. But as you look here, this was kind of his original periodic table. And he organized the elements based on similar properties and began to see some patterns. And so it is from his work that we have our modern periodic table. He organized his in order of increasing atomic mass. The modern periodic table is organized in increasing atomic number. And you can see some places here where he had some gaps, places where he predicted an element to be, but that element had not yet been discovered. And in many cases, he was absolutely correct and could predict the products based on what he expected them to be and the patterns that he saw. So as we explain a lot of these different patterns that we're going to see, it's going to come down to Coulomb's law. And Coulomb's law is written in equation form here, but it's really small, so let me rewrite that larger. The force of attraction, we'll say, is proportional to some constant k times the charge of the first item, the charge of the second particle, divided by the distance squared. And so we're not going to worry about the actual value here of this constant. And we're going to kind of fudge it a little bit as we talk about the charges. This is kind of a physics concept where we might actually have two oppositely charged particles. You can see here we've got one that has a positive charge and one that has a negative charge. And those oppositely charged particles are attracted to each other. And Coulomb's law helps us to determine and identify the magnitude or the amount of that attractive force. That's what I'm going to call the fat. So fat is equal to or proportional to the charge over the distance squared. So the R is the distance between the charged particles. So as the charge on the particles goes up, right, as the value of this numerator gets bigger, the value of that fraction gets bigger, so the attractive force increases. As the denominator of this fraction increases, well, then the value of the fraction also decreases, which would make the attractive force go down. So we have to kind of figure out how these are going to relate to each other and how they're going to relate to properties and the periodic patterns and periodic trends that we see. Coulomb's law, if that denominator gets bigger, the force of attraction gets. So there's a concept called the effective nuclear charge as we're talking about atoms. And really that comes down to the number of protons in the nucleus and how they are attracting the outer electrons. We are most interested in what's going on between the valence electrons and the nucleus. There's a lot of other stuff going on in between. Right? So the blue arrows here represent attraction. Well, if there are inner electrons, well, then there's some repulsion going on between the inner electrons and the outer electrons. Technically, there's also some repulsion going on between the outer electrons, but primarily we are thinking about what's going on, the interactions between the inner and the outer, and then the interaction between the nucleus and the outer. So the effective nuclear charge is kind of the number of protons minus this S term. This is that shielding or screening term. And so you could think of S sort of as the number of inner shells So we're getting a little technical here. It's sort of a calculation that you're never ever going to have to do, but it's sometimes these equations are helpful in thinking about what's going on. So on one level, we would say that these inner electrons shield the outer electrons from the attraction of the nucleus. Well, they don't really block it. It's not as though they get in the way. What's going on is they are pushing the outer electrons away from the nucleus. And if they push them away, going back to Coulomb, smaller. So if they push them away, the effective nuclear charge, or ZEF you might hear it referred to, is going to decrease. I'm not a big fan of using this term. I like talking about protons and energy levels and distance. But I want to introduce this term because you'll see it in the textbook. You'll hear it if you watch other videos. And it's certainly fine to use, but just saying the term effective nuclear charge is not enough. It's not a magic word that communicates a ton of understanding. You kind of have to be able to explain what's going on with the effective nuclear charge. And to me, that means you're talking about number of protons, number of occupied shells, the distance between the protons and the electrons. I think that's a little more foundational in the explanation. You'll see more as we go on. So the effective nuclear charge, or maybe we could just simply translate this and say the number of protons, is going to increase from left to right across the periodic table. Now, number of protons doesn't decrease down the group, but the effective nuclear charge is going to decrease down the group because we are adding more shells. So if we go back to that equation where the effective nuclear charge was equal to the number of protons minus the amount, minus the S, if S is those inner shells, well, then ZEF is going to decrease because the S term is getting larger. So if we talk about the size of an atom, to me that comes down to attraction again. It also comes down to shells, and we'll explore that in a minute. All right, so more occupied energy levels is going to result in a larger radius. So as you go down the periodic table, right, the number of shells is going to increase. Let me back up a second. How do we define atomic radius? It's a very formal definition. Half the distance between the nuclei of two identical atoms that are bonded together. So imagine that this was a hydrogen atom and this was a hydrogen atom, and they're bonded together. Well, if we take the distance between the nuclei, which is what we have here, right, and divide that in half, that is going to be that R radius value that Coulomb's law is interested in. Sorry, back up. Not what Coulomb's law is interested in, but in defining the atomic radius, right? So half the distance. It's kind of a technical definition. Don't get too lost in that. Really, radius means how big the atom is, if that's kind of our working definition. So we know based on the data that the radius decreases across a period and increases down a group, right? So if we go from lithium to beryllium to boron, right, we see the numbers generally decrease as we go across. And then we see the numbers increase as we go down a group. If we look at group 1 here or group 2, we see that they're increasing in all of those groups. So the real question is, well, why? Why does the radius increase as we go down a group? Well, here's a well-crafted answer. Your answers don't have to be this well-crafted, but they do need to contain some of these concepts. All right, so as we go down a group, electrons occupy energy levels that are farther away from the nucleus. What's another way to say that? Well, we keep adding energy levels, right? There are more and more shells that are, keyword here, occupied. And so if we have more shells, physically the atom is getting larger. If you think back to middle school where you had the nucleus and then you had these dotted lines around it, even though this is not the way an atom actually looks, It's sufficient for describing the size of the atom. And so if this is the first shell and this represents the second shell and then the third shell, you can see that as we keep adding shells, the atom is going to get larger. Well, what about across a group? We're not adding shells. If you look at electron configurations, we are only adding electrons to a shell that currently exists. But the number of protons are changing, right? The number of protons are increasing. So we have increasing nuclear charge, right? Another way to say that is more protons. And relatively constant shielding, right? We're not really adding energy levels. There are some sublevels. We go from S to P, and that does increase shielding a little bit in certain spots, but it doesn't affect the radius. So, but as we're increasing the number of protons, but keeping the number of shells the same, the atom is going to shrink. So bring that back to Coulomb's law, where fat is proportional to, we would just say, the charge over the distance. And in this context, charge is number of protons, and the distance is occupied energy levels, right? How many energy levels, how many shells are there in the atom? And again, across a period, the number of shells remains constant. The number of protons increases as we go across. So the numerator is increasing while the denominator is largely staying the same. So the attractive force is getting greater. Well, when an attractive force gets greater, it tends to pull things closer. If it pulls things closer, that means the radius, right? Those shells aren't as spread out as much. They get pulled in tighter. So what about ions? Well, ions follow a similar pattern to atoms. So the pink, let's look at the pink first. So we have a lithium ion. The gray represents a lithium atom. So you can see with the gray, the radius decreases as we go across. That's the atoms. The colored part, though, the pink, well, the cation radius decreases, right? Cation, positively charged. Well, then over here we have anions. And so we start with an anion radius of 1.4 and go down to 1.33. So the cation radius decreases. So let's follow the numbers, 1.34, 0.9, 0.82. But then suddenly, when we switch over to anions, the radius jumped way up, right? It went from 0.82. If we were blindly following a prediction, we would say, oh, oxide ion should be smaller than the boron ion. So it should be less than 0.82, when indeed it's not. It's much, much more, almost double. And you see, as you look at the other periods, that same trend continues, right? The aluminum ion is 0.51, but the sulfide ion, that's more than tripled, right? So it's much bigger. So we need to be able to explain that. What's going on? We can explain why the cation radius is decreasing. We can explain easily why the anion radius is decreasing, but we need to focus a little bit on what's going on next spot here. Well, you know that when a cation forms, electrons are lost. So if we look specifically at lithium, 1s2, 2s1, right? And that is for the lithium atom. I'll take a look at the lithium ion. It's simply 1s2. Well, what changed there? Did the number of protons change? No. The number of occupied energy levels decreased. Again, going back to Coulomb's law. If the denominator is getting smaller, right, charge over distance, right, that denominator is getting smaller, what does that do to the value of the fraction? Makes the value of the fraction increase, right? So the fat, the force of attraction is increasing, and so the lithium ion gets smaller for two reasons. That last remaining electron experiences a greater effective nuclear charge, and maybe more importantly here, there are fewer occupied shells in the lithium ion. That also holds true for beryllium ion versus beryllium. or for aluminum ion versus the aluminum atom. But now let's look at oxygen versus the oxygen ion. So 1s2, 2s2, 2p4, and that's oxygen. 1s2, 2s2, 2p6, that's O2 minus. Well, what happened? Did we change protons? No. Did we change energy level, number of occupied energy levels? No. So why did the radius of the oxide ion become so much larger? Well, this is representing more repulsion. And what does repulsion do? It's going to spread things out. If we're spreading things out, that means those valence electrons are being pushed farther away from the nucleus, which is what's making the radius increase so dramatically. Same argument holds true for fluoride ion and for all of the other anions as well in this. So practice problem here, if we're to arrange the following isoelectronic ions in order of decreasing size. Question 1, what does isoelectronic mean? It means the same number of electrons. Well, if we're doing that, if we're order of decreasing size, so we're going from largest to smallest, well, let's think about that. If they all have the same number of electrons, well, then the largest one should have the fewest protons. And the smallest one should have the most protons. Why do I say that? Well, it goes back to Coulomb's law. Charge over distance. Number of protons over the number of occupied energy levels. Well, the number of occupied energy levels in all of these isoelectronic ions is the same, so it's going to come down to an analysis of the protons. Ionization energy is another pattern that we see in the periodic table. Very technical definition here that you need to pay attention to. It's the energy needed to remove an electron. Right? That's kind of the working definition. The specific details, very important. Where's that electron being removed from? From the ground state of an atom, and that atom is in the gas phase. So I need to put down here that that is gaseous atom, right? Then it's also a gaseous ion. It's going to be a cation because we're removing an electron. So we need to know the period trend. We need to know the group trend. Across a period, ionization energy increases. We could say it gets harder. All right, more energy is required. Down the group, ionization energy decreases. Well, it gets easier. I would prefer you use the terms more energy, less energy. But I'm using kind of the general phrasing here just to help communicate it right now. But it would be better if you would say requires more energy, requires less energy. Those trends. Well, the question then is, well, let's think about it. As we go across a period, what happens to the number of protons? Number of protons goes up. What happens to the number of occupied energy levels? No change. Conclusion about fat, what's going to happen to the attractive force? Attractive force is going to go up. So if the attractive force is greater, that's a reason why it's going to require more energy to overcome that attraction. More energy to overcome the increased fat. Now, fat is not a AP Chem term. That's a my term, right? That I know what that means. So don't write fat on the AP exam. Write attractive force. Okay, what's happening as we go down the period? Well, the number of protons is going up. The number of occupied energy levels is also increasing. So who wins? Well, remember back to Coulomb's law. It's charge over distance squared. So anytime that denominator is increasing, mathematically it's going to have a bigger effect. So therefore, if the denominator is winning, the attractive force is going to go down. And there's your explanation as to why it takes less energy to remove electrons as you move down the periodic table. But why? So some atoms, we can remove one electron or two electrons or three. Well, shoot, if we had enough energy, we could remove all the electrons. As we look at this diagram here, though, it says that the first ionization energy is greater than the second, is greater than the third. I said that backwards. The first ionization energy is less than the second and is less than the third. Why would that be? Again, let's think about Coulomb's law. What's changing? Are the number of protons in the element A changing at all? No, the number of protons are not changing. What's changing? The number of electrons. Is the number of occupied energy levels changing? Maybe. It depends on which atom it is. If this is lithium, or say sodium, yes, the number of occupied energy levels is changing. Simply write out the electron configuration for each of those atoms. Right? So for sodium, after it lost one, after it lost a second, after it lost a third, there's going to be significant changes there because now the outer shell was once an inner shell. The inner shells are always closer to the nucleus. But let's say this was aluminum. Now, there are 3 valence electrons in aluminum. So there's the first one that got lost. There's the second one. There's the third one. Now, if we had another ionization, i.e. 4, right, removing a 4th electron from aluminum, now we're talking about fewer energy levels, but not for the first 3. So what's really going on? Let's look at sodium. 1s2, 2s2, 2p6, 3s1. So a sodium ion, 1s2, 2s2, 2p6. Okay, so why was it easier? So if this is, why is it easier to lose that first electron? Well, it's farther from the nucleus than this one. Right? You could say it's more shielded. It experiences a weaker effective nuclear charge. So the sodium ion, let me make this a clear plus sign here. Right now, to lose an electron from a sodium ion, it's coming from an inner shell, right? And initially, the third energy level was the outer shell. Well, now the outer shell is the second. So the next ion will be Na2+. That'll be 1s2, 2s2, 2p5. Well, why is that harder? We didn't lose any shells, did we? I hope the answer to that was no. Right? But from here, from 2p6 to 2p5, we have less repulsion. All right, so Coulomb's law works 2 ways. All right, it explains attractive forces. It also explains repulsive forces. So we tend to think of it as oppositely charged particles most of the time, but if we think about it also in the context of particles with the same charge, they will repel each other, and more of that same charge will repel more. So in this context here, we're removing negative charge without changing energy levels. So less repulsion leads to more attraction. All right, attraction and repulsion always go hand in hand like that. Let's take a look at aluminum here real quick. And for some reason, I can't get my pen to erase. So here we go. So let's look at aluminum. 1s2, 2s2, 2p6, 3s2, 3p1. So there's aluminum. Well, what's the electron configuration for the aluminum ion? 1s2, 2s2, 2p6, 3s2. Now, we did lose a subshell. And so that might make that might be a reason why the second ionization is larger than the first, right? So fewer subshells, fewer occupied subshells, but there's also less repulsion. What about Al2 plus? Well, that's 1s2, 2s2, 2p6, 3s1. Right, what happened here? Are there fewer subshells? Nope, same number of subshells. So less repulsion. And again, less repulsion means more attraction. Why is it less repulsion? Because there are fewer electrons pushing each other away. So if we look at periodic trends in first ionization energies, let's look at sodium again. So that first ionization energy was 498, and this is probably kilojoules per mole of electrons. So we need 498 kilojoules. To take away a second electron from sodium, we need almost 10 times more energy. That's because it's coming from an inner shell. If we contrast that with aluminum or even magnesium, right? Magnesium, the next door neighbor, right? To take away the first electron from magnesium is 736. Why is that more than to take one away from sodium? More protons. The second electron, taking that away from magnesium, it doubles. That's an increase, but it's not a almost five-fold increase. Yet to take away another electron from magnesium, to take away a third electron, well, now we've got a big jump. Why is there a big jump here? Well, this third electron would be taken from an inner shell. And so as you follow this staircase down here, you see at the staircase the big jumps. All of the other jumps, relatively speaking, are small until you get to taking an electron away from an inner shell. And so you can look at this data and say, based on that big jump, if we didn't know this was sodium, you would say, based on that big jump, I would predict that this element comes from group 1 and must have one valence electron. If we look at aluminum, right? Okay, yeah, that goes up by a factor of 3. Doesn't go up by that much. And then, yikes, we're increasing almost by a factor of 5 here. That's a big jump. So that would indicate that all 3 of these are coming from the valence shell, and that this fourth one is coming from an inner shell. Now, if you remember the electron configuration from aluminum, it did lose a subshell after that first electron was lost. So it's not all that surprising that this increases by a factor of 3. And then the next change isn't as large because it's coming from the same subshell. So if we look at the patterns, we said that in general, across a period, ionization energy increases. So here is period 2. All right, then down here is period 3, period 4, period 5, period 6. Now we've taken the D block out of this. just for simplicity's sake. And so some things might jump out at you here. I hope they do. I hope what jumps out at you are these things right here, right? Places where the trend is not what you would expect, right? Certainly not what you would predict. Well, why is that? Well, let me encourage you, write down the electron configuration for those, right? Identify what atoms we're talking about here. So as we look at these, we've got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then neon. So if we look at the electron configuration of beryllium, so beryllium is 1s2, 2s2. Boron, 1s2, 2s2, 2p1. We expect boron's ionization energy to be higher than beryllium's just because of the pattern, but in reality it's lower. We'll take a look at the electron configurations. Is there maybe something that jumps off the page at you as to why the ionization energy for boron is less than that of beryllium? And if your inclination is to say, yeah, it's got to have something to do with that 2p sublevel, you're right. That is farther from the nucleus or farther from the protons. Therefore, according to Coulomb's law, it's going to experience a weaker attractive force, which would make it easier or require less energy to remove. So as you're going through these again, tie them back to Coulomb's law. Now, what about nitrogen and oxygen? Well, let's look at the electron configurations again. Nitrogen, 1s2, 2s2, 2p3. And oxygen, which we would expect to be greater just following the pattern, 1s2, 2s2, 2p4. Well, nothing jumps off the page right now that would indicate that oxygens should be lower than nitrogen. So we have to look a little bit deeper. So let's look again at nitrogen, except this time I'm going to do an orbital diagram. So there's 1s, there's 2s, and then here's 2p. 1, 2, 3. So if you remember electron configurations, there's the Aufbau principle that tells us what order the sublevels are filled. Then there's Hund's rule that says the electrons are going to occupy the orbitals each in one orbital first before any of them can have two electrons. Why in the world would that be? Right, so this is because of Hund's rule. Not that the electrons know Hund's rule, right? But the electrons will spread out. Why would they spread out from each other? They don't like each other. They're all negative, right? They all have the same charge. They want to be as far apart from each other as possible. So if we are getting farther away, we're minimizing from each other. We're minimizing attraction. We're minimizing repulsion. In doing that, we're maximizing attraction. So this is a minimum repulsion with each other. And that leads to maximum attraction to the protons. So this is nitrogen. Now, if we look at oxygen and we look at the orbital diagram, 1s, 2s, 2p. So there are 4 electrons in the 2p. And so if This arrangement up top represented a minimum repulsion arrangement. They were as spread out as far as they could be. This is not minimum repulsion. And if it's not minimum repulsion, it is not maximum attraction. So attraction has decreased because we're cramming in two electrons into the same orbital, right? That's the non-minimum repulsion thing, right? So if repulsion goes up, attraction has gone down. If attraction has gone down, that means it's easier to remove an electron. That means it requires less energy to remove the electron. The last trend here is in electron affinity. I like to refer to this as electron love. Right? Affinity means you have an attraction for something. Well, we've used that attraction word an awful lot. And so it's the energy change, again, definition here. Energy change when an atom gains an electron. That's kind of the working definition. The very strict definition requires that atom to be in the gas phase. And so we'll be making a gaseous ion in each of these cases. And so in the first case, where we are gaining an electron and becoming an anion, in that instance, the delta H, or the energy, or this is technically called enthalpy, you can simply use the word energy in its place. The enthalpy, or energy change, is negative. If you remember that from last year, that is called exothermic. Energy is released. In the second example here, the enthalpy change is positive, and that is endothermic. That means energy is required. So in one instance, energy is required to make the atom gain an electron. In the other instance, the opposite is true, that energy is not required. And so we would say energy is released. Under what circumstances would gaining an electron require energy? Well, an atom that's not very as attracted to electrons might require energy in order for it to gain. Whereas this atom up here is very attracted, so much so that it happens naturally. So one of the things that I've always said is that in all of the universe, there's kind of one fundamental law that things seek the lowest potential energy possible. You might phrase that as things want to be stable, right? That's what lowest potential energy means. The lower the potential energy, the more stable it is. And so things that lose potential energy, that happens in a natural way. Examples I've given in the past of that are a ball is going to naturally roll down a hill. And as it rolls down the hill, it loses potential energy. Right? That energy is released in the form of kinetic energy. If you pick somebody up above your head and drop them, they will fall back down to the ground. Above your head, they had high potential energy. And when they get back to the ground, they have reduced their potential energy. They had to release some energy in order for that to happen. But in order for you to pick that person up over your head, energy was required. You had to put energy in order to raise them up off the ground, up over your head. So in general, electron love increases when moving from left to right and decreases moving down a group. And so we look at some of the values here for electron affinity. And so down a group, the number becomes less negative. That means it is a decreasing electron affinity. I know that the negative numbers sometimes mess us up. Remember that negative is not telling of the magnitude, it's the negative means that the energy is released, and the positive means energy is absorbed. So the positive ones would be like beryllium or magnesium. They require energy in order for an electron to be added. Let's look real quick at the electron configuration of beryllium versus lithium. So lithium again is 1s2, 2s1. So beryllium is 1s2, 2s2. When lithium gains an electron, if it were to gain an electron, and it's attracted to electrons, so it could, right? It would become lithium with a minus charge. Don't get hung up on that and say, wait a minute, I thought you told us that metals become cations, so it should lose an electron. Very true. We're just exploring a different concept here. When given the option, lithium loses because it's easier for it to lose than it is for it to gain. It's going to go to that lower potential energy state. And the losing the electron gets to a lower energy state than gaining. But if it does gain, it's going to go into an existing sublevel. It's going to become now 1s2, 2s2. Beryllium, when it gains, where does that next electron go? Well, it's going to have to go into a higher energy sublevel. Remember the terminology with the Aufbau principle, that electrons fill orbitals of lowest energy first. So the 2p sublevel is a higher energy sublevel or subshell. So in order to get into that higher energy subshell, that's going to require energy. That's why that's positive there. Same thing for magnesium. It's going to have to go into a higher energy subshell. Some other positives. Well, we see it again here. Not surprised with nitrogen and oxygen. Remember that nitrogen was P3. So to become P4, now an electron has to be added into an already occupied orbital. That's going to increase repulsion. So in order to get it there, energy has to be absorbed by the system. What about the noble gases, right? Group 18 or 8A. Well, let's look at helium. That's simply 1s2. If helium becomes an ion, that's 1s2. Where does that extra electron go? Not just a higher energy subshell, but a whole new shell. One of the reasons why noble gases are unreactive is because it takes so much energy for them to gain an electron, because it's got to go in a higher subshell, or to lose an electron, because as we go across the period, the number of protons increases, but the amount of shielding or occupied energy levels stays the same. And so it becomes increasingly more difficult to lose an electron once you get to that full subshell. There's nothing magic about a full subshell. It all has to do with energy. And so here's the example with helium. All right, now before you start in on the id with yid, I just wanted to go through the we do part with you so that you're prepared. So rank the following from smallest to largest atomic radius. So we've got a sodium ion, a sodium atom, a sodium cation, a sodium atom, and a sodium anion. Well, all three have the same number of protons. And we want to go from largest to smallest, smallest to largest radius. Well, the smallest radius for A had better be the sodium ion. How do I know that? Well, because in order to become an ion, I can find it here on the periodic table, right? It lost the 3s electron, and now it only has 2 occupied subshells, or excuse me, 2 occupied energy levels. Na will be next. And then Na minus. Well, why is Na minus bigger than Na plus? It's got the same number of protons. It's got the same number of occupied shells and subshells, but it's got more electrons. More electrons mean more repulsion. More repulsion means electrons are being pushed away from the nucleus. That means less attraction. It means it's going to get bigger. How about B? Carbon to nitrogen to oxygen. Carbon, nitrogen, oxygen. Well, if we follow the pattern across the period, oxygen is going to be the smallest, carbon is going to be the largest. Same number of occupied energy levels. Oxygen has more protons, so it's going to be smaller. Chlorine, argon, and krypton. Excuse me, chlorine, argon, and potassium. So that's chlorine, argon, potassium. Well, which one is the largest? Well, potassium should be the largest because it has 1, 2, 3, 4 shells. So I'm going to put potassium down here on the end. Which one's going to be the smallest? Is chlorine or argon going to be the smallest? Now, argon should be the smallest. It's got more protons than chlorine does. So chlorine will be in the middle. And then D, let me change pen colors here. We'll go red. We've got beryllium, magnesium, calcium. Now this is just following the pattern. The smallest should be beryllium. The largest should be calcium. And that's simply because we go from 2 shells in beryllium to 3 shells in magnesium to 4 shells in calcium. Thanks for sticking with me. Good luck on the IDWIDYD. We'll talk more next week.